Let's get started with today's material. So, first thing we'll be talking about today are the extreme values of a function and the extreme value theorem. Intuition, what are the extreme values of a function? They're basically the highest points the function reaches and the lowest point the function reaches. Extreme values.
Can the extreme value be infinity?
No. So let's get an exact definition. Let f be a function with a domain D. Then f has an absolute max slash min, so we're doing two definitions in one, has an absolute max slash min value on D at some point C, provided that, in the one case, if we're talking about the max, it's a max if f of x is less than or equal to f of c everywhere in the domain. Good so far? When is f of c the absolute max? When it's greater than or equal to the value of the function at every point in the domain. That's when it's the max point.
Okay.
Is this notation throwing you off?
No.
Okay.
Yeah, I think we're good.
Or if we're talking about the absolute min, what's the absolute min? That's at a point C if f of c is less than or equal to f of x for every point in the domain. Then it's the absolute min. Lowest point the function reaches or the highest point the function reaches.
So it's a point?
Yes. Reaches it's a value at a point. It reaches its max at some point C if f of c is greater than or equal to the function at every other point.
Okay.
So it's the value of a function at a point.
So what happens if the domain is infinity?
We can have an infinite domain and still have an absolute min.
What would be the absolute max if I had an infinity domain?
Depends on the function. We're not saying every function has this. We'll see when functions have this. That will be the extreme value theorem. The value f of c, whether it's a max or a mix, whether it's a max or a min, is called an extreme value.
Okay.
So if I'm talking about an extreme value, you know I'm talking about either an absolute max or an absolute min, an extreme value. And that's why the section is called extreme values. Okay, so let's do an example really quick to help give some intuition for this. So let's look at the function y equals x squared with the domain negative infinity to infinity. So just per hour, right here, y equals x squared.
Okay.
What's the minimum value that function reaches?
0.
0. What's the maximum value the function reaches?
Infinity.
It doesn't have one.
Oh, so it's
So
just
it has a min, it doesn't have a max. Good?
Yeah.
Okay, let's restrict the domain now. Let's look at it from 0 to 2. So now we're looking at this function starting here and ending here. Get rid of the rest. So now our domain's just 0 to 2, so here's what our function looks like, right? What's the min value?
0.
What's the max value?
2.
Perfect. Now, let's make our domain 0 to 2, not including 0. So now we have an open point here. Open point. Now what's the min?
The limit as x approaches 0.
The limit as x approaches 0 of this function is 0. But the function isn't defined as 0. What's the min?
0.
It's not 0. It never reaches 0.
Yeah. You can't say it's not just the limit.
The limit is 0. The point of limits was, you can talk about the limit of the function even if it wasn't defined at the point, or defined how you wanted it at that point. What's the min?
Really small and close to 0.
Really small and close to 0, so maybe like 0.01?
No, because you can go smaller.
Smaller? How small?
Smaller.
Infinitely small.
There
Oh,
isn't a min,
so, okay.
is the point. There is no min. Okay, but what's the max?
2.
Wonderful. And then finally, if we do open interval 0 to 2, so we don't include 2, what's the min?
Undefined.
Doesn't have one. What's the max?
Doesn't have one.
Doesn't have one. Perfect. there is no point in this domain that satisfies this condition, and there is no point in this domain that satisfies this condition. Okay, so I think you have some good intuition for what this is talking about. So now the extreme value theorem. If f is continuous on a closed interval, AB, it's very important that that's a closed interval. Notice that when we use a closed interval, we had a min and max, right?
What if you do a closed interval around infinity and negative infinity?
What are you talking about?
Oh, you can't do that. No,
Okay.
Never mind.
Okay, so if it's a closed bounded interval like this, 0 to 2, or in other words, 0 to b, or a to b for a general one, then f has an absolute max and an absolute min, call them big M and little m, somewhere inside of there.
Okay.
Okay? That is, there exist 2 points, x1 and x2, in the domain, such that f at one of those points is a minimum point, and f at the other of those points is a maximum point.
Wouldn't that just
So
be
little m is less than or equal to f of x is less than or equal to big M on that entire interval.
Wouldn't the max and the min just be A and B?
Not necessarily. We'll see some more examples.
Okay.
So let's come look at some examples. Oh, mean value theorem. We're not actually going to prove this theorem because it uses an axiom on the real numbers that we haven't talked about called the completeness axiom. And so proving it is something that's left to the class we call real analysis.
Okay.
So if you want to see a proof of that, we're skipping over it not because you couldn't understand it, it's just because we'd have to make so much reference backwards and work back up that it would be a lot of work for a little bit payoff. Okay, so let's see it in action. Here's some continuous function. Notice I can draw this without picking up my pencil. It's continuous.
Mm-hmm.
It starts at some point A and it ends at some point B, so it's defined on a closed bounded interval. The intermediate value theorem says it must somewhere on that interval achieve an absolute max, and it must somewhere on that interval achieve an absolute min.
Yeah.
Which does. Here's its absolute max, here's its absolute min. Notice that those are not the points A, B.
I see.
Another example. A, B, some continuous function. In this case, it does achieve a max at the point f of A, and it does achieve a min here, f of B. Another example. Notice it achieves a max here, and the min is over here at A.
Yeah.
So only one of them was an endpoint, one of them was somewhere in the middle.
I see.
And then here we have our min is somewhere in the middle, and our max is one of the endpoints. So we've seen all 4 cases. The max and the min are in the middle, the max and the min are in the endpoints, the max is in the middle, but the min is an endpoint, the min is in the middle, but the max is an endpoint.
What happens when it's like cosine just goes up and down, up and down, up and down?
So you're saying we've got something like this, right?
Yeah.
Assuming all these are the same height, and assuming all these are the same depth, any one of those is an absolute min, and any one of these is an absolute max.
So you pick either.
Because it satisfies the condition. Look at the condition. Every point x is less than or equal to f of c.
Okay.
If I pick the point, if this is a sine function, and we pick the point pi halves, sine of x is always less than or equal to sine of pi halves. Right?
Mm-hmm.
So it works. Satisfies the condition. Any other questions? Okay. It's a pretty straightforward concept. Just looking at maxes and mins. Okay, now we also have a notion of a local max and a local min. Not just an absolute max and an absolute min. So as we're looking at this function, here's its absolute min, here's its absolute max, right?
Yeah.
But notice it achieves like a local max right here and a local min right here.
What do you mean by local?
What do I mean by local? Intuitively, it means if there's some interval of the domain I can pick such that this acts as a max or that this acts as a min.
That makes sense.
So here's exactly what it means now. If there's any open interval I can pick around that point such that that point is now a max on that open interval if there exists any open interval. Where that's the case, it's a local max. Similarly, if there exists any open interval containing this point D such that D acts as a min, it's a local min.
So you could have like thousands of them?
You could have thousands of them, but not on this. On this, your only local max and local mins are right here, 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 and here.
Can't you make,
Pick any open interval right here.
yeah.
Now it's an open interval. No max, no min, because we don't include those points.
What do you mean you don't include?
Oh, because it's on a curve.
Because open interval, not close, open. A, B, not including the endpoints. Come back to here. Remember what happens when our domain was 0, 2.
Yeah,
And we didn't include those. What was the max, what was the min?
there isn't one.
There isn't one. So if you do an open interval on just some slice of a function, typically you're not going to have a max or a min.
But if you do it around a point,
But if you do it around a local min, like right here,
okay,
then you will have a min. You won't have a max, but you'll have a min. So notice if I pick this interval, then on this interval, this is a min.
I think I see it, but I'm still a little lost in how you can have an open interval around the local min and then not one around any part on that function.
You can have an open interval anywhere you want. The point is that most open intervals do not have a max or a min.
Yeah, so how does
An
it
open interval will have a max or a min if and only if you're talking about something that could act as a local max or a local min.
Okay, how does that work though? Like, you can put this open interval anywhere, right? And then you just put it around this local min or local max and it just works?
If there exists any open interval, I can place around this point,
Okay,
such that this point now acts as a min. It's a local min.
that it acts as a min.
Yes, if I can restrict the domain to an open interval around that point, to make this a min, it is now what we call a local min, by definition. Similarly for this, I can find some domain, some restriction of the domain to an open interval around C, such that this is a max.
Okay, I see that. How does the endpoint work then? Because you can't put an open interval around that.
You sure can. You have to intersect it with the domain. If you go back to thinking about topology, when we had a closed set and we intersected it with an open interval, the intersection was still an open interval in the subspace topology. So we can take the open interval around that point. We can take an open interval around A and restrict the domain. Well, A is an endpoint.
Yeah, okay.
So what happens when I restrict the domain to this interval? I'm left with this. A to some point, epsilon.
I see.
So it still works.
Okay.
Okay, so now let's read the definition and hopefully it makes perfect sense. A function little f has a local max or min at some point C in the domain D, provided that f of x is less than or equal to f of c, or f of x is greater than or equal to f of c for all x in some open interval containing that point C.
Okay.
Does that definition now make perfect sense?
Yep, that makes sense.
Okay. And then just for the sake of this picture here, what I'm trying to draw right here, I'm trying to make this kind of pointed so that there's no derivative at this point.
Why are you trying to do that though?
Just to make it very clear to you that this is talking about when the function is just continuous. It doesn't necessarily have to be differentiable everywhere. So I could have also used the absolute value function. Absolute value does have a min there, even though it doesn't have a derivative there.
So
So
what's
it's a
the
property of
point-
continuous functions.
What's the point of extreme values pertaining to derivatives then?
Well, we'll see how they come into play. We'll use this theorem to prove some stuff. So the point is we're only using the fact that it's continuous. Nothing about being differentiable. Make sense?
Mm-hmm.
Okay, so now let's do a quick proof. And you'll see how it's connected. If f has a local max or min at c, some point c in its domain, and if the derivative at c is defined,
So if there is one.
so the derivative exists. So we can't be talking about a point like this. We could be talking about a point like this. So this so far is a valid point for something that we're talking about here. With me?
Mm-hmm.
So, and if f prime of c is defined, then f prime of c is equal to 0.
And where do you prove that?
So look at your local maxes and mins or your extreme maxes and mins. We're going to show that if a derivative exists at those points, then the derivative must be 0. Yeah, we're going to prove that.
Because there's no slope.
Yeah, so hopefully it makes intuitive sense. Here the derivative has to be 0 because it's like the top of a hill. Here the derivative has to be 0 because it's like the bottom of the hill.
Yeah.
Derivative doesn't exist at this point, derivative doesn't exist at this point, derivative doesn't exist at this point.
Mm-hmm.
Come back to a picture like this, go to our max, derivative was 0, look at this, derivative was 0. All our maxes and mins on this scene, derivative 0, 0, 0, 0, 0, 0. So hopefully it makes intuitive sense. Okay, so let's do the actual proof now.
Okay.
So 1, assume f of c is a local max. We'll just handle the case of local max. Proving it for local min is identical.
Okay.
Assume f of c is a local max on some open interval ab. Right? That's how you have to prove it's a local max, is there has to be some open interval containing c such that f of c is a max on that interval. Right?
Mm-hmm.
Okay. So then I know that on this open interval, f of x is less than or equal to f of c, since f of c is a local max. You with me so far?
Mm-hmm.
So looking at our picture here, we could be talking about, we already have an AB on this, let's just erase all these points so that none of them are named. If we're talking about this point, here's C, then A is this point and B is this point. Some open interval AB containing C. Okay. So I know f of x is less than or equal to f of c on this whole interval. Okay, now what else do I know? Side note, come back over here. I know that if the limit exists at a point, I know that if the limit as x approaches c of f of x is equal to L, if the limit exists at a point, then I also know that the left-hand limit and the right-hand limit are both that same thing.
Yeah.
C from the left is equal to L, and as x approaches C from the right is also equal to L, right? If the limit exists at a point, then the left-hand limit exists, the right-hand limit exists, and they have to give you the exact same value. You with me?
Mm-hmm.
Okay, so here's what I'm going to do. I'm going to take, oh, we're talking about a max, so we're talking about over here. So here's C, here's A, here's B, here's our open interval. Right?
Yeah.
Okay, so here's what I'm going to show. I'm going to show that the derivative as we approach from the left is greater than or equal to 0. Okay. Notice it's slanted up.
Mm-hmm.
I'm going to show that the derivative as we approach from the right is less than or equal to 0. So if the derivative is greater than or equal to 0 and it's less than or equal to 0, what's the derivative?
It's equal to 0.
It's equal to 0. Right?
Mm-hmm.
Because my left-hand derivative and my right-hand derivative have to be the same thing since they're limits if the derivative exists. And we know it's given to us. F prime of c is defined. That's a given.
Yeah.
So I know the derivative exists. So my left-hand derivative and right-hand derivative have to give me the same value. Okay. So we'll start with taking the left-hand derivative. So then f prime of c is equal to the derivative as x approaches c from the left. That's a c with this minus sign up here. The limit as x approaches c from the left is equal to f of x minus f of c over x minus c, right?
Mm-hmm.
Compare the signs of these really quick. If I'm approaching c from the left, which means my x's are over here, what's x minus c?
X minus C?
What's the sign of it? Is that a positive number or a negative number?
It's positive.
It's negative. C is bigger than x. If I do a
Oh,
smaller
yeah.
number minus a bigger number, because x is approaching from the left, so my x is like right here. Here's C.
Okay.
So x minus C, this is negative. You with me?
That's saying it's from the right.
I'm approaching from the left.
I know, but your notation, the C plus says it's right.
We're doing this.
You're pointing at the other one.
Oh, sorry. Not that one, this one.
But that's saying it's greater than 0, not a negative.
So x, just stick with the denominator for now. X minus C is negative.
Yeah.
Okay, so we got negative in the denominator. Let's look at the numerator. I know what about f of c?
F of C,
Uh-huh.
that it's the max.
That's a local max. So I know f of c is greater than or equal to f of x everywhere on this interval.
Okay.
So f of c is greater than or equal to f of x. So if I do f of x minus f of c, what's this?
It's either 0 or a negative number.
It's 0 or negative. So it can be negative or it can be 0. Right?
Mm-hmm.
Negative over negative is,
Positive.
so the whole thing is either positive or 0.
Okay.
So the whole expression is greater than or equal to 0. Follow the logic there?
Yep.
Okay. Now let's look at the right hand. So now our x is over here. Right? And we're approaching from the right. So looking at that one, x minus c now is
Positive.
positive. F of x minus f of c is
Negative.
negative or 0. Same thing as before, right?
Mm-hmm.
So we either have a negative over a positive, which is,
Negative.
or we have 0. So it's less than or equal to 0.
Okay.
Therefore, the derivative is 0.
Why is it? Oh, you're right.
Make sense?
Yeah.
And then if you do the limit for local min instead of a local max, it's almost identical.
Okay.
It's just going to flip the signs on both of these.
That makes sense.
Good?
Mm-hmm.
Okay, so we just barely proved if you have a local max or local min, the derivative is 0 at that point.
Yeah.
And we also proved, we didn't prove, but we stated prior to that, if you have a continuous function on a closed bounded interval, it has a local max and a local min.
Yeah.
Mm-hmm.
So it has derivatives equal to 0 somewhere in there.
Or not.
Unless it's the endpoints.
Yeah.
Correct. Okay. Ready to move the camera now, right?
Mm-hmm.
No more questions about any of that stuff? Try and turn it to get some of those graphs in case you still need them. I shouldn't have messed with that. So sticky. Okay. We did that. Now we're doing this. Okay. An interior point. An interior point C inside of D, of a domain, some domain D, of F, is called a critical point now if the derivative is 0 at that point or the derivative is undefined at that point.
An interior point meaning any point inside of it?
Yes, C meaning not endpoints.
Not endpoints. Gotcha.
So interior point meaning you can't include endpoints. Not talking about endpoints, ignore the endpoints. Any other points now. So any points that aren't endpoints, we call them critical points, provided that the derivative at that point is 0 or the derivative at that point is undefined.
How is the derivative going to be undefined?
Come back to this picture.
Okay.
The derivative was undefined here
Oh, I see.
because we made it a sharp point. Looking at the absolute value function, the derivative is undefined here.
I see.
So looking at this whole function, here's a critical point, here's a critical point, here's a critical point. That's what we mean by critical point. Any interior point where the derivative is 0 or the derivative is undefined.
Okay.
Okay, so there we go. Now we know what a critical point is.
So what's the difference between a critical point and a local min or local max?
Give you one example of one really quick. Looking at the cubic function. So looking at y equals x cubed.
Okay.
So if we look at that function, it looks like this.
Yeah.
This point right here, 0, is not a local max or a local min, but the derivative is 0 there.
Okay.
And to validate that the derivative is 0 there, how do we do that? Take the derivative really quick. Y prime is equal to 3x squared. Plug in 0. What do you get? 0. The derivative of this function at 0 is 0.
Okay.
Okay. But it is a very real possibility that if your derivative is 0 or undefined, then you are talking about local max or local min. It's a very real possibility. So let's use derivatives now to try and find some local maxes and or absolute maxes and mins really quick. So find the absolute max and min of f of x equal to x squared on negative 2 to 1.
Okay.
Now we already know, just because we're familiar with the parabola, what the answer is. The absolute min happens at 0, the absolute max happens at negative 2. But let's think about it in terms of the information we have here. So we know that the max or min is going to happen where the derivative is 0, the derivative is undefined, or at the endpoints. So those are the 3 places we need to check.
Okay.
Check where our derivative is 0, or where our derivative is undefined, or the endpoints. And our maxes and mins have to be at those points. So those are the only points we have to check in looking for our maxes and our mins.
Okay.
Does that make sense?
How do you check at a point that's undefined?
Where the derivative is undefined. The whole function has to be continuous on its domain for any of this to work.
Yeah.
So the function is defined everywhere. The limit of the function exists everywhere. Remember, if a function is continuous, that means the limit as x approaches c of f of x is equal to f of c. So this happens everywhere on our functions that we're going to be talking about. They're going to be continuous functions.
So it's already.
So notice that the function was still continuous here. The derivative just wasn't defined there.
I see.
So we're talking about the derivative not being defined. So we're looking at points where the derivative is 0 or the derivative is undefined.
Well, still, how do you find where the derivative is undefined?
When you take the derivative, the same way any function is undefined. When is a function undefined? When you have to divide by 0 or take the square root of a negative number.
Yeah.
That's where it's undefined. Right? If I take my derivative and I get something like x minus 1 over x squared plus 1, if this is what I get when I take my derivative, where is it undefined? Negative 1.
No, that's 2.
Oh,
Yeah, that doesn't work. There you go.
Negative 1
And 1.
well, the 1 will cancel out with the numerator, and then the negative 1 is where it will still be undefined. Actually, yep, you're right, both. Because we can't just cancel out. So it has a hole, this function has a hole in one place and a horizontal asymptote in another place.
Okay.
So if that's your derivative function, then you see 2 places where there's problems, where it's undefined. And so it's possible that your function has a max or min at those points. Possible, not necessarily the case. That's all we're saying. Now that's not how it's going to be when it happens. What will happen is your derivative from the left will give you one number, your derivative from the right will give you another number. Like what happens with your absolute value. Your derivative from the left is negative 1, your derivative from the right is 1, and so the limit at that point, when we're talking about the derivative, at that point doesn't exist.
I see.
Okay, so let's look at this now. We're looking for the max and min. What do we got checked? Derivative 0, derivatives undefined, endpoints. Those are the 3 things we need to check. So what is our derivative? What is f prime of x?
Just 2x.
Just 2x. Where is 0 equal to 2x?
As 0.
When x is 0.
When x is 0. And that's always defined. It's never undefined. right?
Yeah.
Yeah, you can't find.
So the only points we need to check are 0, -2, and 1. I'm guaranteed that my max and mins reside at these 3 points. So these are the only 3 points I need to check.
Okay.
So now, it's just a matter of checking those points. What's f of 0?
0.
0. What's f of 1?
1.
And what's f of -2?
4.
Okay, so this is the smallest of them, so that's my absolute min. This is the biggest of them, so that's my absolute max.
Okay.
Yep.
Make sense? Let's do another example, one that's a little bit more complicated.
Okay.
All right. So same thing. Find the absolute min and max of this function g of t equal to at minus t to the 4. I'm guaranteed the min and max are either at the endpoints or where the derivative's 0 or where the derivative's undefined. The derivative's never going to be undefined in this case. So let's find its derivative, right?
Mm-hmm.
So what's g prime of t?
8 minus 4t cubed.
Oops. Perfect. So where is the derivative equal to 0? So that's going to happen when, move this over to the other side, divide both sides by 4, when t cubed is equal to 2, right?
Yeah.
Or t is equal to the cubed root of 2.
Okay.
What? Why? Doesn't that make it 8 times 4?
8 times 4.
If I plug this value in for t, my derivative will be 0.
If you
So really quick, what's the cubed root of t cubed? Sorry, what's the cubed root of 2 cubed?
2.
Just 2, right? Like the square root of 2 squared is 2. The cubed root of 2 cubed is 2. So when t is equal to the cubed root of 2, t cubed is 2. Times 4 is 8. 8 minus 8,
Oh.
0.
Okay.
So it's where the derivative is 0.
Okay.
Follow that?
Yeah.
Where else is the derivative 0?
Where else is the derivative 0?
Yeah.
I don't know. Isn't that the only place you can?
Nowhere else.
Okay.
But we could have had a derivative that had multiple zeros. So don't stop just because you find 1 0. Make sure you find all of them. We found all of them, so we're good. So t equal to that could be one of our max mins, and then the endpoints, -2 and t equal to 1. So these are the 3 points that we need to check
Yeah.
for our absolute max and absolute min. So let's check those points. What is g of the cubed root of 2 equal to? Let's plug it in. We get 8 cubed roots of 2 minus, you okay with me just saying 2 cubed roots of 2?
Yeah.
Notice this is 3, or this is cubed of them, leaving 1 more left over. So here's t cubed times t gives me t to the 4.
Okay.
Writing it this way. Okay? And that is equal to 6 times the cubed root of 2.
What? Oh, I see.
You have 8 of them here. If you get rid of 2 of them, how many do you have? 6.
Okay.
Okay? So that's g at the cubed root of 2. Now let's look at g at 1. What does that equal?
7.
Try again. Oh,
Yeah, 7.
7. You're right. 7. And then what's g at -2 equal to?
0.
Is that 0? Let's see. -16 minus 16.
16, so -32.
Minus 32. So here's our min for sure. Which of these is bigger?
I'm gonna go with the 6 times cube root 2.
6 times the cube root of 2. I'm not positive which of those is bigger. So you'll have to plug that into your calculator. Where's my backpack? Right here. Six times 2 to the 1/3. 7.56. So,
So it is
this one. So this is slightly bigger than this. So here's your max, here's your min.
Okay.
Okay? Let's do another one. F of x is equal to x to the 2/3 on negative 2 to 3.
Okay.
Alright. Take the derivative of this, what do we get?
2/3 x to the negative 1/3.
Yeah, so let's write it this way. 2 over 3 times the cube root of x, right?
Mm-hmm.
You okay with me writing it that way?
If you explain how you
2/3 x to the negative 1/3.
Okay.
Good?
Yeah.
Okay. So now, where's the derivative equal to 0?
When x is 0.
Oh, I just realized. Cubed root of 2 is outside our domain here. So our max is at 1, and our max and min were the endpoints on this one.
Oh, because that isn't inside the domain.
Because this is not inside the domain.
And so you have to go, okay.
That makes sense?
Is the cube root bigger than 2?
The cube root is bigger than 1. Cube root of 2 is bigger than 1. Because what's the cube root of 1?
1.
1. So the cube root of 2 has to be bigger than 1. Make sense?
Mm-hmm.
So we actually said that one wrong, so g of 1 is our max up here, and g of negative 2 was our min. Okay, so remember to make reference back to the domain that you're actually talking about.
I see.
Okay, anyways, where is this derivative equal to 0?
When x is 0.
When x is 0, the derivative 0?
Oh, no. When x is 0, it's undefined.
When x is 0, it's undefined. So x equal to 0 is one of the places where we could have a max or a min.
Okay.
But where's the derivative 0?
There isn't one.
It's not. Wonderful. So there's nowhere where the derivative 0. We found a point where the derivative is undefined. So we need to check that point. And now we need to check the endpoints.
Okay.
And notice that x equal to 0 is in our domain this time. So make sure to pay attention to that. So x equal to negative 2 and x equal to 3. There's the 3 points we need to check for our max or our min.
Okay.
Okay. So now let's check them. What's f of 0 equal to?
0.
0. What's f of negative 2 equal to?
I don't know.
You can give me something.
I don't know how to do that algebra.
You can take the cubed root first and then square it, or you can square it then take the cubed root.
What's
So
the cube root of?
X squared?
Which is?
Cube root of 4?
Perfect. So cubed root of 4.
Okay.
And then what's f of 3 equal to?
The cube root of 9?
The cubed root of 9. Now what's our max, what's our min?
0 and cube root of 9.
0 is our min, cubed root of 9 is our max.
How is the cube root of 9 bigger than the cube root of 4?
What's bigger, 4 or 9?
Yeah, but doesn't the Q? No, sorry. Okay. Okay.
Okay. So there were some examples finding max and min. Now you feel like you could do these problems easy, no problem?
Sure hope
No
so.
problem to do the problem?
We'll see.
All right. So now let's get to our next section, which is on the mean value theorem. And we'll start with a theorem called Rolle's theorem. I'm guessing just named after the mathematician who found the theorem. Okay, mean value theorem. Let's give it to you in a nutshell what the mean value theorem says. Mean value theorem in a nutshell says, if I have a function, some function doing whatever it's doing, pick 2 points on the function. Well, I have a function defined on a closed bounded interval AB. So we'll just look at the function on AB.
Okay.
Let's look at the slope between the points A and B. So draw this secant line. A secant line is just a line that intersects at more than 1 point. Tangent line intersects at 1 point, secant line intersects at more than 1 point. So don't be confused when I say secant line. When I say secant line, I just mean the line that intersects these 2 points.
But not.
It's called a secant line.
Still straight.
Secant?
Secant line, yes, as in our secant function.
Oh.
I didn't go over with you all the trig functions and how they get their names. If that's something you're really interested in, we could talk about that after class or something like that.
Okay.
But it gets its name because the secant line intersects a circle twice when you draw it. Anyways, so here is the line that goes through the point A, B, right?
Okay.
We have some continuous function defined on the closed interval AB, and now we have a line that goes through the points just AB. With me so far?
Mm-hmm.
What does the mean value theorem say? The mean value theorem says that there must exist a point somewhere in between A and B, and in this case it's going to be somewhere like right here, such that the slope at that point is equal to the slope of the line through these 2 points. So a line parallel to this line.
So the tangent line is parallel with the secant
So the
line?
tangent line at some point is parallel with the secant line through the 2 endpoints.
Okay.
Another way that you can interpret that as saying is this is the average slope between these 2 points, right?
Mm-hmm.
Here's the average slope between those 2 points. What that says is the instantaneous slope has to equal the average slope somewhere in between those points.
The instantaneous slope?
Yes, the instantaneous slope, the slope at a point,
So the tangent?
has to be equal to the average slope of the whole interval.
And you're saying there has to exist a point that does that?
Yes.
Okay.
Let's give a more real-world application of this. Let's say that I know that you went from here to Salt Lake. We'll say that that's 300 miles, just to keep the math simple.
Mm-hmm.
And we'll say that you did that in 6 hours. What was your average speed?
15 miles an hour.
Yeah.
50 miles per hour, right? So if we were to plot that, you started out here, plot however you were moving until you got to Salt Lake. Your displacement would be 300 miles over 5 hours. This would be 300. And you just calculated the slope of this line, which was your average speed, right?
Mm-hmm.
So what is the mean value theorem? Your actual curve for how you moved might be something like this, who knows?
Okay.
What it means is that since your average speed was 50 miles per hour, it is guaranteed at some point in that journey, you were driving exactly 50 miles per hour.
For real?
Yeah. Think about it. You have to be going 50 miles per hour at some point, because either you went exactly 50 miles per hour the whole time, in which case you were going 50 miles per hour at some point, or if at one point you were going slightly less, at another point you had to be going slightly more.
You had to pass.
And you have to pass 50 miles per hour to go more than 50 miles per hour.
Oh, I see.
So it makes pretty intuitive sense once you think about it.
Okay.
Mean value theorem. Mean value theorem says that the slope at a point has to be equal to the average slope on the whole closed interval at some point. We'll write out the exact mean value theorem.
Okay.
Okay, but that's what the whole section's about. Mean value theorem. Pretty famous theorem.
Don't we use this in physics a lot?
You use it in calculus a lot, and calculus is all you use in physics. So
Okay.
Well, that and trig and algebra, but yeah. Okay, so before we get to the mean value theorem, we're going to prove just a special case of it called rule theorem. Here's what rule theorem says. If y is equal to f of x, some curve, so if f of x is a continuous function on a closed bounded interval ab, and it's differentiable on the open interval ab, so the derivative exists at every interior point, maybe not the endpoints, but at every interior point the derivative exists. That's what we mean by differentiable on ab. And if f of a is equal to f of b, so the function starts and ends at the same height, so draw a picture of what this might look like. Here's a, here's b, here's f of a and f of b. They're the same height, so it starts and ends at the same height. I have no clue what it looks like in between, but whatever it looks like in between, it has to be continuous and differentiable.
So it's kind of like the sine function?
Who knows?
Okay.
It could have been a straight line, it could have been something like this, it could have just gone up and down. Who knows? Something. That's kind of not a function because I backtracked a little. Oops. But it does something. We don't know. With me so far?
Mm-hmm.
So it's differentiable on the open interval AB, and f of A is equal to f of B. The endpoints are equal to each other. Then there must exist some point C in the open interval AB. There must be some point C somewhere in here. Don't know where, just somewhere in there. There must exist C in the open interval AB such that the derivative at C is equal to 0. That's what we're proving.
Okay.
Now it's a special case of the mean value theorem because if f of A is equal to f of B, what's the average slope on the whole function?
0.
0. So we're saying the instantaneous slope at a point somewhere on the interval has to be equal to the average slope of the whole interval still. We're just doing it for the special case of 0.
Okay.
With me so far?
Mm-hmm.
All right, so let's do the proof here of Rolle's theorem. Since f is continuous, then f must have a max min on the closed interval AB. That's going back to our extreme value theorem. We know f is a continuous function and is defined on a closed bounded interval AB. Therefore, it has to achieve a max and min somewhere on that closed interval AB.
An absolute maximum, right?
An absolute max and min somewhere on the interval.
Okay.
It could include the endpoints, or it could be interior points.
Mm-hmm.
Right?
Yeah.
Now, since f is differentiable on all of AB, then the max and min are where f prime is equal to 0. For some c in AB, or they're at the endpoints AB.
Yeah.
Right? Remember, we had 3 cases to check. Where could our absolute max and min be? Where the derivative is 0, at the endpoints, or where the derivative is undefined. We got rid of the case where the derivative is undefined by definition. We said a function that is differentiable everywhere.
Okay.
So we get rid of that case. So now there's only 2 places where our absolute max and min can possibly be. At an interior point where the derivative is 0, or at the endpoints. And that's it. You with me?
Mm-hmm.
Okay, so that's what we're saying then. So since f is differentiable on AB, then the max slash min are where the derivative is equal to 0 for some interior point, C in the open interval AB, or they're at the endpoints, A and B. Right?
Mm-hmm.
So, if the max min are the 2 endpoints, notice, sorry, I should have been more explicit when I said this. So if the max or min are one of the interior points, the derivative is 0 there, and we're done.
Say that again?
What are we trying to show? We're trying to show that there exists some point C in the interior AB where the derivative is 0. That's what we're out to do.
Mm-hmm.
Okay.
So if the max or min are an interior point, if they're somewhere between A and B where the derivative is 0, then the derivative is 0 there.
Yeah.
So if the max is an interior point, we're done. The derivative is 0 there. If the min's an interior point, we're done. The derivative is 0 there. We've already shown that.
But now we need to show.
So now the only case that we need to handle is the max and min are both the endpoints.
Okay.
So, since f is differentiable, if the max and min are any interior points, the derivative 0 there, and we're done. If the max and min are the endpoints, then since f of a is equal to f of b, then f of x is now a constant function. That's the only way for the max and min to be the endpoints, because the max and min are the same height. So the whole function has to be greater than or equal to f of a, and the whole function has to be less than or equal to f of a.
Okay.
And the only way for the function to be greater than or equal to f of a and less than or equal to f of a is for the function to be f of a constant function.
Yeah.
So, if we're saying the only way that the max and min aren't somewhere in some interior point, if we require them to be the endpoints, then our function has to look like this. A constant function, where the height is f of a or f of b.
Oh, where it's just a horizontal line.
Yeah, constant function. Here's a, here's b, so stop defining it after that, and stop defining it before that. So if a max and min show up anywhere on the interior points, we already know the derivative 0. If they don't, and the max and min are the endpoints, our function has to be a constant function.
I see.
And what's the derivative of a constant function?
0.
0.
Yeah.
Everywhere.
Yeah.
So then, for any c you pick in there, f prime of c is equal to 0.
Mm-hmm.
So, in either case, we found a point C where f prime of c is equal to 0.
Okay.
Okay.
So we showed that if f of a is equal to f of b, there has to be some interior point called c such that f prime of c is 0.
Mm-hmm.
That's what we just showed.
But what if the endpoints are on like a slant, like in that other picture?
We're handling just a special case where f of a is equal to f of b.
Oh.
Special
So
case.
So how does it work for every other function?
Yeah, we'll prove it in general.
Okay.
What's called the mean value theorem, and we'll prove the general one. You just use Rolle's theorem to prove the general theorem.
Okay.
So what we'll essentially do is take any random function now and adjust it so that it fits into Rolle's theorem, and then I'll show you. It's not that hard. Understanding Rolle's theorem is harder than understanding the actual theorem, I think, because the actual theorem is Rolle's theorem. But before we do that, let's just use Rolle's theorem to show how it's already useful. Let's show that x cubed plus 3x plus 1 has one and only one real solution. So x cubed plus 3x plus 1 equal to 0. We're looking for solutions to that. We're going to prove that this has one and only one solution.
Okay.
With me? So first off, let's show that it has a solution. What do I get when I plug negative 1 into this thing?
Negative 1?
Mm-hmm.
Yeah.
So let's pretend that that's called f. What's f of negative 1 equal to?
Negative 1.
Negative 3. Or
Negative 3, right? Negative 1 minus 3 is negative 4, plus 1 is minus 3.
mm-hmm.
Oh. I see.
Right?
Yep.
Now let's look at f of 0.
That's 1.
1. So, going way back to our intermediate value theorem, since our continuous function is equal to negative 3 here and equal to 1 here, it has to be equal to 0 somewhere in between negative 1 and 0.
Okay.
Yeah.
That was using something that we did a couple weeks ago. Probably last week. Intermediate value theorem.
Okay.
So I now know that there exists, I'll call it A, I don't know, maybe C. There exists C in negative 1 to 0, such that f of C is equal to 0, right?
Mm-hmm.
So I know that there's at least one point where this function is 0.
Okay.
Now I'm going to prove that there's only one point where this function is 0.
How do you do that?
How do I do that? Let's look at f prime of x really quick. What's f prime of x equal to?
3x squared plus 3.
Right? Where is this equal to 0?
Yeah. No.
When x is equal to,
It's not.
can you, yeah, I don't think you can find it.
It's never equal to 0.
But you just said it was.
No, I said where is it equal to 0? And it never is equal to 0. So what does that mean? So think about if this function f equals 0 at another point. So we know it equals 0 at some, we'll call this a actually. I know it equals 0 at some a, where a is in here, right? If there existed some b such that f of b was also equal to 0, if that were the case, then by Rolle's theorem, the derivative would have to be 0 somewhere in between.
Yeah.
But I know the derivative is never 0. Therefore, f of b can't exist. So there is no second solution.
Okay.
So I know that there's one solution. I know that there's one place where the function is equal to 0. If there were another place where the function is equal to 0, then the derivative would have to be somewhere equal to 0 somewhere in between those 2 points, using Rolle's theorem.
Yeah.
But the derivative is never 0. So there can't be a second point where it's equal to 0. In other words, if you have a function whose derivative is never 0, it can cross the x-axis at most once. If the derivative is always positive, if the function is always increasing, it only gets to cross the x-axis once. Because it's always going up.
Yeah.
It has a positive slope. Always. Everywhere. So it can only have one solution.
What's the solution?
Somewhere between -1 and 0. We don't care what it is. We were just proving that it only has one.
Yeah.
But I thought there wasn't one because the derivative can't be 0.
We know that there has to be, look, f of -1 is equal to -3, f of 0 is equal to 1. So I know somewhere between 0 and -1, there has to be some point A such that f of A is equal to 0. So I know that. So there is one solution, for sure. The question is there a second solution? And that's what we showed is impossible. We said, let's pretend that there is some second solution, call it B, where f of B is equal to 0. Let's pretend that there is one and see if it's even possible. You with me so far?
Yeah.
So if f of b equals 0, and f of a we already know is 0, now we found 2 points where the function is 0. Or 2 points where the function gives the same value. By Rolle's theorem, that means the derivative has to be 0 somewhere in between. But the derivative is never 0. So this point can't exist.
Okay.
Follow the logic now?
Yeah.
Okay. Any other questions?
I'm good.
Okay, so now I think we're ready to prove the mean value theorem. We'll just prove it and then I'll see what the book actually does and maybe we're getting ahead of it. So let's now prove the mean value theorem. I should probably find it in the book just to make sure I get my verbiage exactly right for what's given to us. Actually, it's going to be the same as that, so I can just write it like that. So mean value theorem proof, what are we going to do? We're going to prove that if y equal to f of x is continuous on closed interval AB, closed interval AB, differentiable on the open interval AB, and we don't need to require f of a equal to f of b. That's all we need to require. If we have that and differentiable on the open interval AB. And then there must exist a C in the open interval AB such that f prime of C is equal to the average slope from A to B. What's the slope from A to B? That's going to be f of B minus f of A over B minus A, right?
Yeah.
Rise over run. Change in Y over change in X.
Okay.
Good with that?
Mm-hmm.
Okay. So mean value theorem. This is the mean value theorem. Here's what we're going to prove. So I'm going to let me draw a picture to help make sure you see what I'm overall thinking. So here's our curve. Here's F. Here's A. Here's B. And then we're going to have some, I'm going to define a line that goes through here and call it G of X. So I'm going to define this line right here to be G of X. So let G of X equal, what is that line that goes through A? This is f of A, B, f of B. What is the line that goes through those 2 points?
The secant of that one.
But what's the actual equation for the line?
G of x equals mx plus b. I don't know what you're asking.
How do we get the equation of a line to a point? When you've been finding the tangent line, the equation you've been using is y minus y1 is equal to m times x minus x1, right?
Yeah.
This is the equation of a line that passes through the point x1, y1.
Okay.
I want the equation of a line. I can get my slope from these 2 points and require it to go through this point. I'm going to call that line g of x. So I'm going to do instead of minus y1, I'm going to do my plus y1 over here. So I'm going to write it this way. You okay with that?
Yeah.
And then, well, that's a fine way to leave it. So g of x is equal to m, what's my slope? What's the slope of that line?
I don't know what the slope is.
Yeah, you do. What's the change in height?
The distance between f of a and f of b.
Which is what? Give it to me as an equation. How would you calculate it?
F of a minus f of b.
Other way, f of b minus f of a.
Yeah.
And what's the run?
B minus A.
B minus a. Okay, there you go. You calculated a slope. Woo! You ready for pre-algebra?
Okay.
M x minus what?
x1
Which is, in our case,
f of a.
Or
Or
A.
just a.
Yeah.
Hey, you better correct that. Don't make me yell. And what's our y1? F of a.
Okay.
This is the equation of a line with this slope that goes through this point.
Okay.
We could have also used this point as a point to go through. Gives us the exact same line.
Yeah.
Okay,
Okay.
there we go.
Okay.
We got the
Right.
equation of a line.
Right.
You guys have been supposedly calculating a lot of tangent lines.
No.
If you can't calculate a tangent line, you'll stand a chance on the test we're doing today.
That's why I need help. Oh,
You're in trouble. Okay, so there's our line. Let g of x equal that line. 2. Now I'm going to define a new function. Let h of x equal f of x minus g of x.
why are you doing that?
Why on earth would I ever do that? What is g of a equal to? the height of G at A?
Where
F of A. Notice that you could also just plug in A for X. This whole thing goes away and you're left with F of A. Right?
A for X.
Look at G of X is equal to this thing, right?
Mm-hmm.
So what's G of A equal to? Replace your X with an A,
Times 0.
Oh, 0.
which leaves you with.
F of A.
But you can also tell it just from the picture. What's the height of our line at A? It's F of A, right? What's the height of our line at B?
F of B.
F of B, right?
Yeah.
So, if I define H of X, so it's equal to F of X minus G of X, what does H of A equal?
F of A minus G of A.
Which is
0.
0. And what does H of B equal?
0.
0. So now my H has a special property that we wanted for Rule's theorem. The only difference between the mean value theorem in general and Rule's theorem is Rule's theorem says F of A equals F of B. Well, now I defined H so that H of A is equal to H of B.
I see.
With me?
Uh-huh.
Now we need to do the algebra to show that H of A is equal to H of B. H of A, you can see how that comes out to 0. H of B, let's make sure that you can see how H of B comes out to 0 with the algebra.
Okay.
So I'll say, let H of X equal this, comma, and denote H of A equal H of B equals 0. And then really quick, let's just show you that H of B is for sure 0. It's easy to see H of A because it's easy to plug A into that and see that that all goes away and you're left with F of A. It's not as obvious that when I plug B into this, I'm going to get F of B. So that's really what we need to see. So let's just make sure that we can see how G of B is equal to F of B. And then I think we'll be good to continue. Right? So G of B. Let's calculate that. That's going to be F of B minus F of A all over B minus A times X minus, times B minus A plus F of A, right?
Yeah.
Notice that B minus A cancels out with B minus A down here. So you're left with F of B minus F of A plus F of A. F of A and F of A go out, you're left with F of B.
Gotcha.
So G of B is just equal to F of B. You see that?
Yeah.
Okay. So now, with that, I think it'd be easy enough for you to, I think that's enough for you to see H of A is for sure equal to H of B.
Okay.
Because G of A is for sure equal to F of A and G of B is for sure equal to F of B.
Yeah.
Okay. So, 3. Then, by Rule's theorem, there must exist C in a B such that H at C, H prime at C is equal to 0.
Yeah.
Mm-hmm.
That's using Rule's theorem. Now, what is H prime of C? H prime of C is equal to, what is the derivative of C? Or the derivative of H?
It's the derivative of fx and gx.
It's the derivative of f of x minus the derivative of g of x.
Okay.
Is equal to f prime of c minus g prime of c. Right?
Mm-hmm.
Which gives me that, since h prime of c is equal to 0, which gives me that f prime of c is equal to g prime of c.
Okay.
Because h prime of c is equal to 0. So move this to the other side, and you get this. You with me so far?
Yeah.
So, 5. Then, f prime of c. Notice that we don't know anything about that. But g, we know exactly what g is. We can calculate its derivative. What is the derivative of g?
I don't know, that's
This is just g of x is equal to m times x minus a plus f of a. This is just a constant. This is just a number.
Okay.
Where's our only variable?
X.
Right there. Take the derivative of this with respect to x. What do you get?
Just
1 minus a.
just x.
Oh my goodness. Alright, let's write it out like this. If I have y is equal to m times x minus a plus b, what's the derivative?
1 times x minus 1 plus 1.
Alright, let's do a little bit more algebra. Y is equal to mx minus m times a plus b. Okay, now what's the derivative?
It's
Just m! What's the
X
derivative of
times
b? 0.
0.
What's the derivative of m times a?
0.
0. It's a constant.
Yeah.
What's the derivative of mx?
M.
Just m.
Okay. Okay.
Looking back at this whole thing, I have a constant times x minus a constant times a constant plus a constant. So the only thing I care about is a constant times x. Take that derivative, get rid of the x, I'm left with just my constant, m.
Okay.
You see all that?
Yeah.
So, f prime of c is equal to what?
F of b minus f of a over b minus a.
Perfect. Which is what we were trying to prove. That there is a point c such that the derivative at c is equal to the average slope.
Okay, I see it.
That's all we were after. There exists c in a b such that f prime of c is equal to the average slope.
Okay.
So, if you drive from here to Salt Lake, you do it in 6 hours, you are for sure going 50 miles per hour at some point in the drive. There may be multiple points in the drive, but there must exist at least one point in the drive where that is the case.
Okay.
That's what we just proved. Alright, so let's get back to the book, see what the book does. Imagine we just have a bunch of example problems to do now. Roll theorem, we proved that. We did example 1. The mean value theorem. Oh, so the author did prove that next. Okay, so we're around track. Okay, so now he does an example problem. Example, the function f of x equal to x squared on 0 to 2. So we're looking at, so doing an example here, we have f of x is equal to x squared on 0 to 2. Okay, so we're supposed to prove that this function has a slope of, let's see, what's the average change of this function from 0 to 2?
2x.
What's the average slope of the function?
2.
Not 2.
Yeah.
Where does it start? What's the height of the function at 0?
0.
0. What's the height of the function at 2?
4.
4. So what's the average slope of the function?
4.
4.
But it's going to
Divided by 2.
Which is 2.
Which is 2.
Yeah, that's what I said.
So the slope, the average slope, m is equal to 2. So according to our intermediate value theorem now, our mean value theorem, there must exist some point between 0 and 2 where the derivative of this function is equal to 2.
Okay.
Picture really quick of what we're doing. Maybe that will help. 1, 2, 1, 2, 3, 4. Talk about parabola. Goes like this. Right?
Yeah.
We know the average slope from here to here. If you draw that line has a slope of 2. So we need to find the point in between here. Some point in between here, C, such that f prime of C is equal to 2.
Okay.
We know by the mean value theorem that there must be such a point. Now let's find the point. So what's the point going to be?
1.
It's going to be just 1. So f prime of x is equal to 2 of x. Where's 2 of x equal to 2? At x equal to 1.
Oh, that's easy.
So C is over here at 1.
Okay, can we do a more complex one?
We'll follow just the examples that he does, and then if you want to do more complex stuff after that, we can do that as well.
Okay.
If a car accelerating from 0 takes 8 seconds to get to 352 feet, so let's write down our information here. So I'll use S, V, and A for my functions here for position, velocity, and acceleration. So I know that S of 0, the position of the car at 0 is 0, and the position of the car at 8, after 8 seconds, is 352. With me so far?
Yeah.
So if a car accelerating from 0 takes 8 seconds to go 352 feet, its average velocity for the 8-second interval. So now what's the average? Our average change?
Just 352 divided by 8.
352 divided by 8, which is 44. But good, you knew how to calculate it.
Okay.
So the mean value theorem says that at some point, the car was going 44 feet per second.
Does it want us to find it?
No, because we don't know what our function s is.
And you
We
can't-
have no clue what this car looked like. All we knew is it started, and 8 seconds later, it had gone 352 feet. So what is some information we know about that car for sure? We know for sure that at some point in that drive, that car was going exactly 44 feet per second.
Okay.
All right, corollary. If the derivative is equal to 0 at each point x on an open interval, then the function is a constant function. Okay, so let's do that one. So we know that the derivative of a constant is always 0.
Did you finish that first problem?
Yeah, that was it.
Mm-hmm.
We know that the derivative of a constant is always 0, but is it true that if you have some secret function, and I know its derivative is 0, then your secret function is just a constant?
We need to prove that?
Yeah, how would you just know that? If it's a constant, the derivative 0 doesn't tell me that if the derivative 0, it's a constant. We've never proved that.
Yeah.
That's like doing a backwards derivative.
Why are you getting at?
Huh?
I said, why are you asking us?
Well, we're going to prove it.
Oh.
We're going to prove that if you have some function whose derivative is always 0, then your function is a constant. And it's like doing a backwards derivative. We're figuring out what f is when we know what f of prime is.
Okay.
Does that make sense?
Yeah.
We're actually calculating our first integral, kind of.
That's how you figure out integrals?
Yes, integrals are the inverse of derivatives. So if I know that the derivative with respect to x of x cubed is equal to 3x squared, which I do,
Yeah.
then I know that the integral of 3x squared with respect to x is equal to x cubed plus a constant. And I don't know what the constant is. Could be 0, which gets us back where we started. So, gets us there within a factor of a constant.
Why a
Which is-
constant?
Undo.
We're about to show y a constant. But yeah, they undo each other.
Okay.
Notice now, if I take the derivative of this, what do I get?
3x squared.
3x squared. So notice, x cubed isn't the only function whose derivative is 3x squared. X cubed plus any constant you choose will give me 3x squared. So there's a whole family of functions whose derivative gives me 3x squared. And that's x cubed plus any constant you want.
Interesting.
So there's a whole bunch of integrals, there's a whole bunch of functions out there whose derivative is 3x squared. What are all those functions? They're all these functions. These are all the functions, pick any constant you want, whose derivative gives you that.
Okay.
So if I know the derivative of a function is equal to 3x squared, then I know the function must have looked like this. We happen to start with just x cubed plus 0, we could have started with x cubed plus 5.
Same thing.
Well, they're within a constant of each other.
Yeah.
They give the same derivative, yes. So now what we're going to prove is if the derivative is everywhere 0, then the function you have was a constant function. What constant? We don't know, just a constant. Could have been 10, could have been 0, could have been 2000. The derivative of all those is 0. Okay. So, the proof that we're doing, if f prime of, let's see how they say it, if just f prime of x is equal to 0 at each point x in an open interval AB, if f prime of x is equal to 0 for x in AB, well, for all x in AB, for all x in some open interval AB, comma, then f of x is equal to some constant c on that open interval AB. I think that's all it says. If f prime of x is equal to 0 at each point x of an open interval AB, then f of x is equal to a constant c for all x on AB. Yeah, we have that same thing written there. Okay, so let's prove this really quick.
Okay.
I know that f prime of x is equal to 0 everywhere on this interval, which means I know the derivative exists everywhere on this interval.
Mm-hmm.
So I now observe the limit as x approaches x naught, doesn't matter what point we're talking about, but just some point x naught in AB, that the limit as x approaches x naught of f of x minus f of x naught over x minus x naught is equal to 0 for x naught in AB, for any point we pick in there, right?
Yeah.
I know that this must be equal to 0, which means that f of x minus f of x naught, this limit, well, I'm restating the exact same thing. This is equal to 0. When is this equal to 0?
Any point.
In the interval.
Let's actually use our mean value theorem for this real quick. So we're not using limits, because actually, when I'm taking a limit, it's okay for things to go to 0. So let's just say by mean value theorem, observe that, what do I know? I know that f prime at some point c, inside of there, is equal to f of b minus f of a. Is that still going to give me what I want? I know that the derivative is equal to 0. And I know that the derivative is equal to, at some point, is equal to f of b minus f of a. Let's see what they do. They just pick 2 points. Oh. Get my closed interval first. Sorry. Starting again. Let x1, comma, x2 be any 2 points in AB such that x1 is less than x2. So AB is some open interval pick x1 and x2 out of there. And now I have a closed interval that's inside that open interval that I can talk about. Because I need a closed interval to use my mean value theorem,
Gotcha.
which I actually erased. Okay, there we go. So now, 2. So by mean value theorem, comma, there must exist C in this interval between x1 and x2 such that f prime of C is equal to f of x2 minus f of x1 all over x2 minus x1, right?
Yeah.
Now keep track of what we're after here. What am I trying to prove? I'm trying to prove that f is a constant function. That's what I'm trying to prove, right?
Mm-hmm.
So I'm trying to prove that for any 2 points in f you choose, any 2 points x1 and x2 in f that you choose, then f of x1 is equal to f of x2. If this is true for any 2 points you choose, then our function is a constant function. Every input gives the same output.
Mm-hmm.
So we pick 2 random inputs, and we just call the smaller of them x1.
Mm-hmm.
Yeah.
My job now is to show this is true,
Mm-hmm.
using the fact that the derivative is 0. Okay, so I know that there must exist some point C where the derivative is equal to f prime of C, but what is f prime of C?
0.
0. For the whole function, the derivative is 0, so at C, the derivative is 0. So then 0 is equal to f of x2 minus f of x1 all over x2 minus x1, right?
Mm-hmm.
Now when is this equal to 0?
When f of x2 is equal to f.
When the numerator is equal to 0, right?
Yeah.
A fraction is equal to 0 where the numerator is equal to 0. So if this whole thing is equal to 0, that implies, or another way you can think about it is, okay, now multiply both sides by x2 minus x1.
Yeah.
That still leaves 0 over here. So we get 0 is equal to f of x2 minus f of x1, which gives me that f of x1 is equal to f of x2. Which gives me that f of x is equal to a constant. And we're done. Follow that?
How'd you
Yeah.
go from f of x1 equals f of x2 to a constant?
To f of x is equal to a constant?
Yeah.
I just barely showed that for any 2 points you choose, x1 and x2,
Mm-hmm.
the function has the same value at those points.
Okay.
So if we do like a picture, so we don't know anything about our function, well, we just picked, here's A, here's B. So our function is defined on an open interval a, b. Pick any 2 points you want, x1 and x2. We just already showed that f of x1 is equal to f of x2. But that's true for any 2 points you picked. So you could have picked this point and this point. So then that value is the same. Well, now we could have picked these 2 points. So now that's the same value as that. Now we could have picked these 2 points. So that value is the same as that. Now we could have picked, I don't know, doesn't matter, any 2 points, and we keep getting over and over again this line. Make sense?
Yeah.
So our function is a constant function. So we just really showed if the derivative is 0, then your function is a constant function, which, well, yeah. Okay. So derivative of a constant is 0, and if the derivative is 0, then you have a constant. That's what we now know. All right, let's look at another corollary. If the derivative is the same at each point, then the functions differ by at most a constant. So let's give intuition for what this is saying, and then prove it. And we'll do just a concrete example again. So let's look at trying to think about what function gives me this derivative. So I tell you f prime of x is equal to 2x.
Okay.
What is the function f of x that gives me that as a derivative.
X squared plus a constant.
X squared, but x squared plus any constant you could possibly think of.
Yeah.
So what we're proving here is, maybe right to the side here so you can see how this is saying the exact same thing. Proof. We're doing a proof that if f prime of x is equal to g prime of x, for all x in some open interval a b, comma, then there exists some constant big C such that f of x is equal to g of x plus c. Or, in other words, f of x, or g of x minus f of x, or sorry, f of x minus g of x is equal to a constant. They differ by only a constant. So if f of x is equal to g of x plus c, notice that f of x minus g of x is equal to c. That's what I mean by they differ by a constant.
Can't f of x have a constant too?
Sure, but think about it, if you had f of x, you're thinking about for this one right here, right?
Yeah.
So let's say that I know that, some concrete examples real quick. So let's say I know that f prime of x is equal to 2x and g prime of x is equal to 2x. So they have the same derivative, right? Then f of x is equal to x squared plus some constant, we'll call it a. G of x is equal to x squared plus some constant, we'll call it b. Then f of x minus g of x is equal to a minus b. What on earth? Someone standing there?
That was sketchy. What is it?
Now it's out there, so some kid just running by, I'm sure, thinking they're being clever. All right. Anyways, so notice f of x minus g of x is a minus b. Now just call that c.
Okay.
A minus b is just a constant, so if we do c equals a minus b, then f of x minus g of x is equal to c, some constant.
Okay.
So that's what we're proving. If f prime of x is equal to g prime of x on this interval, then there must exist some constant such that f of x is equal to g of x plus that constant, or in other words, they differ by just a constant. So notice we're not just saying what f of x is, we're just saying f of x is the same thing as g of x, differing by some constant. Make sense?
Yeah.
Okay, so let's prove this now. So, proof 1, let h of x equal f of x minus g of x. Good so far? 2, then h prime of x is equal to what?
Constant. Or 0.
Is equal to 0. How did you get there so fast?
As f prime of x is equal to g prime of x.
Yeah, so it's equal to f prime of x minus g prime of x. And then you said, oh, but notice that those are the same thing, so it's equal to 0.
Yeah.
That's what you were thinking in your head, right?
Yeah.
Okay, so h prime of x is equal to 0. So then, h of x is equal to what? If its derivative is 0, then it is a
Constant.
constant. Wonderful. So h of x is a constant, but by definition, h of x was equal to f of x minus g of x.
Okay.
You follow that?
Yeah.
Yeah.
That's it.
Yep.
So we just barely show that the integral, if they have the same derivative, then the integral differs by a constant. So that's why when we say that the integral of 2x dx is equal to x squared plus some constant. That's all the solutions whose derivative is 2x.
What is the little box you do with that?
Oh, that's just what you do at the end of proofs. You used to put QED, so it used to be QED, which was some Latin phrase which meant, and thus it is demonstrated, or something like that. And then QED, that's a lot of writing, so obviously we want to replace that with a box. So you do a box at the end of your proofs, shorthand for, and thus it is demonstrated. We finished what it is we were trying to prove. So it's very helpful, like when you're reading your textbook, because then it signifies the end of where a proof started very explicitly.
Yeah.
So sometimes even when I'm reading this book, I pass over a proof without realizing it until I see that box. I'm like, oh, whoa, I'm in the middle of a proof here. So it can be very useful. Okay. So example, find the function f of x whose derivative is sine of x and whose graph passes through 0, 2. So I'm trying to find the function. What do I know about the function? I know, so we're doing an example here. So put that, so no, something new. So I'm trying to figure out what my function is. I have two pieces of information about my function. I know its derivative is equal to sine of x, right?
Mm-hmm.
And then I know it passes through the point 0, 2. Which means when I plug in 0 as an input, I get 2 as an output. So I also know that f of 0 is equal to 2.
Okay.
So I know its derivative is this, and I know that when I plug in 0, I get 2. My job is to try and figure out what f is.
Okay.
With me so far?
Yeah.
Okay. So
Okay.
what function has a derivative sine of x?
Cosine of x plus
What's the derivative of cosine?
negative sign.
Negative sine.
Negative,
So
sorry.
it's negative.
Negative.
So no negative cosine. So I know that f of x is equal to negative cosine of x
Plus a constant.
plus a constant. Right?
Yeah.
Because the constant will go out when we take the derivative. So these are what all the possible solutions for f of x are if f prime of x is equal to sine of x. With me so far?
Mm-hmm.
But we have our second piece of information which will help us figure out what that constant is. We have what we call an initial condition. So I know that f of 0 is equal to 2. Right?
All right.
So in other words, 2 is equal to what I get when I plug in 0 to this. Right?
Okay.
Mm-hmm.
So, what is cosine of 0? 1. Right?
Yeah.
So what's c equal to? 3. So f of x, my answer is f of x is equal to negative cosine of x plus 3.
Okay.
Okay.
Pretty cool, huh?
Yeah.
That's neat.
Knowing the derivative, knowing how the function slopes, and one point that it goes through, is enough for us to figure out exactly what that function was. We knew its slope everywhere, we knew just one point that it went through, and that's enough for us to reconstruct the whole function.
That is pretty cool.
A lot of information.
A lot.
And notice that, in terms of physics thinking, if you think about f of x as our position function, and then f prime of x would be our derivative or would be our velocity function, that's the same thing as saying that if I know how fast you're going, if I know your velocity everywhere, sorry, this is t, not x, velocity at a time and position at a time. If I know your velocity everywhere, and I know your position at one time, I can figure out your position everywhere.
Okay.
That's cool. That is cool.
Same thing, right? So, common problem in physics, you know the velocity of something, You know its position at time equal to 0. Find its position at time equal to 10.
Okay.
Common type of problem. That would be the problem for throwing this marker. If I tell you the velocity I give this marker, so I throw it, I tell you the velocity I give it, and you know at time 0 it's here in my hand, you should be able to tell me where the marker is going to be in 2 seconds.
That's pretty cool.
And so a common demonstration that you do is like set up little marble shooters. You carefully measure the velocity as it comes out of the marble shooter. And then you can go and you can say, if you launch this marble out of here, you can go find exactly where it's going to land, go put a little bowl there and shoot it into the bowl.
Is that how people do like trick shots, in a sense?
If they're using a little shooter,
So it's always exact.
not always exact, it's physical things and it's hard to get the shooter to release the exact same time each way. There's always a margin of error, but within a margin of error you can do it, depending on how good your equipment is.
Yeah.
Yeah. Okay, and he kind of has a similar discussion. So, makes the connection back. So that's 4.1 and 4.2.
Okay.
So, we're done for today and our recording.